in this lesson, we're going to go over acid-base strength and equilibrium law. We're going to look at two examples and the calculations involved. This builds on what we already looked at when we were doing ice tables in the equilibrium section. So if we look at this first example, we've got an acid ionization constant for nitrous acid, and we're asked to calculate the concentration of hydrogen ions for a given concentration of solution. If you think about what's going on here, we can write this as either the acid base, as the Arrhenius formula reaction, or we can write this as the Bronsted-Lowry formula. So either one of these says what's going on, that the nitrous acid is breaking down into hydrogen and or hydronium ions and nitrite ions. So the difference being that in the Arrhenius version here, we don't have water, and in the Bronsted-Lowry, we have the water that is accepting the proton to become the hydronium ion. Either way, though, if we look at our ice table, we're going to end up including the same things. Because the water is a pure liquid, right, it's not going to be one of the things that we're counting. So either way, our initial is the acid itself, and the ions are 0 and 0. The change, well, it's a one-to-one reaction no matter what we're doing. So on the acid side, we're losing an unknown amount, so we'll say negative x. And on the ion side, we're gaining that same unknown amount. Again, because it's one-to-one, we're just using x. So our equilibrium concentrations then become the concentration of our acid minus x and x for the ions. So 0.250 minus x for HNO2, and for the two ions, x and x. So if we put that into our Ka expression, as I said, the water doesn't make any difference because it's a pure liquid. That's also true for the Ka expression. So we have our ions on top because it's products on top, and our acid or reactants on the bottom, all to the exponent 1 because we have a one-to-one reaction. So if we look at what we know, we've got the value of Ka, and we've got our equilibrium concentrations in terms of x. So we can plug that into our equation. Give me a moment. My computer is deciding to be stally. So either version, we end up with that Ka constant, 5.6 times 10 to the minus 4, right, which is just our equilibrium constant. The A is just indicating that it's for an acid. And then we have our concentrations that we put in there. And so then it's a matter of solving this equation. So first thing we got to do is get rid of that denominator. So we're going to multiply both sides by that. Which is going to cancel out. Whoops, not there. Here. So then we actually have to do that calculation for the left-hand side. It would help if I typed in the right number there, sorry. That should be a 5, not a 4. So 0.25 times 5.6 times 10 to the minus 4 is going to give us 0.00014, and x times 5.6 times 10 to the minus 4 is just 0.0056x. And on the other side, we just have x times x, so we get x squared. We can see that this does work out to a quadratic, so we want to move everything to one side. And now that we do have everything to one side, we can solve that quadratic equation. So it's been a while since we did one of these with the quadratic formula. So quick reminder what our quadratic formula is. Negative b plus or minus square root of b squared minus 4ac all over 2a. So we're going to plug in b is 0.00056, a is 1, and c is 0.00014. So we plunk that in. And then we solve it. So to solve that, some people are going to be comfortable plugging that whole thing into their calculator as one giant equation. But if you want some intermediate steps, I'll put those up here. So our intermediate steps, which you may show or not, I've put in kind of a light gray, maybe too light. Maybe I should change that. Let me just format that a little bit darker or a different color. How about we put them in blue? All right, so all those ones in blue, if you want those extra steps in there, definitely they're optional to put in there. See, I missed my equal signs. Let's fix that. So then when we get to this point, we can see we have a negative minus number or a negative plus a number. So the negative minus a negative is going to give us a negative overall. And we know we can't have a negative concentration, so we can ignore that one or eliminate it. Or the positive one works out to 0.011555, etc. Obviously, I've got a few extra digits there. That is not our final answer, that's just x. Right, so we can ignore that negative answer, as I mentioned, because we can't have negative concentration. But then we end up with our other answer, which is our x, which is our 2 ion concentrations. So rounding that, if we look, our original numbers, the 5.6 only had 2 sig figs, so we're going to round that to 2 sig figs. Don't forget to put units, right? This is concentration. And then to find our other one, we have to put it back into that formula, which is the 0.250 minus x. Just a quick reminder where I'm getting that from is the equilibrium line of our ice table, right? It was 0.250 minus x. So we're going to plug that in for the HNO2 calculation and get a number there. Now we're looking at decimal places because we're subtracting, not sig figs. So we've got 3 decimal places and 3 decimal places. So we actually end up gaining a sig fig from that perspective to get our 3 sig figs there. And remember, with all of these ones, you can check them by plugging it back in to see if you still get the same value of Ka within that last sig fig, which in this case would be 2 sig figs. So if we plug that in with those rounded numbers, and I see I left it unrounded a little bit to plug it in, we do end up a little bit off, but we're really close to that 5.6 times 10 to the minus 4, so we can be pretty confident of that answer with that check. So if you need to go back and look at that a little more slowly, definitely go back and check those answers out. Check those steps out, I should say. But I am going to move on to example 24. So if we look at this one, it's pretty much the same steps. But something happens on this one that lets us take a bit of a shortcut because we don't have to end up doing the quadratic formula. We can, but this is one of those things where if you can take a shortcut, why not? So the first step's still the same, write the equation in one form or another where it breaks into its ions. So I'm going to put it with the Arrhenius version. And so we end up with 0.2 minus x for our equilibrium of the acid, X and X for the two ions. So if we plug that into our Ka formula, we end up with something very similar to what we had a moment ago, which is that we have those values, and I see I missed putting one part of it, which is the 4.4 times 10 to the minus 7. So when we plug that in, because it is 4.4 times 10 to the minus 7, that is a really small ionization constant. And our rule of thumb for where we call it really small is 10 to the minus 6 or smaller, right? So 10 to the minus 7 is smaller than 10 to the minus 6. So if we have one that's that small, we can make a bit of an assumption. Sorry, just going to change the color here to match the rest of it. So basically what we're saying with this is X is so tiny when we subtract it from 0.2, it's not going to make any difference. So this is an assumption, which means that when we get to the end of our calculation, we are going to have to check our assumption. I will say, though, that when it is less than 10 to the minus 6, the vast majority of the time this assumption works out pretty well. So what we end up doing with that assumption, when we re-put this into here, right, so we're replacing Ka with 4.4 times 10 to the minus 7. X times x becomes x squared, but we've made this assumption that this x is so tiny that this bottom just becomes 0.2. So when we do that next step, where we multiply both sides by 0.2, we don't end up with a quadratic because, well, I guess technically it is a quadratic, but we don't have to solve it the same way because we just have x squared on the one side. So we can just take the square root of both sides. Right, so we multiply by 0.2, and then that gives us 8.8 times 10 to the minus 8 on the one side, and the 0.2's cancel on the other side, so we just get x squared. And then, so to solve that, we can just take the square root, which technically gives us plus or minus 0.0003, and again I'm keeping 2 sig figs because my Ka was 2 sig figs. Again, we can ignore the negative value. So we've got our value for x, but what we need to do is check if that assumption we made earlier is correct. So we assumed that x was significantly smaller than the 0.02, or in other words, it's insignificant when we do the subtraction. So when we do that subtraction, we get 0.199970, but if we're rounding to 2 sig figs, it rounds to 0.20. So the assumption that it was so tiny holds up, right? It's not changing our 0.20. So now we can look at that x as being the correct answer for our ions, which gives us our hydrogen ion concentration. That was only part of the question, though, because if you look back to the question, A was calculate the hydrogen ion concentration, but B is calculate the pH. So from there, we're just plunking it into our pH formula. Which is going to give us 3.52 or 3.53, depending on if you plugged in the rounded value. Ideally, you want to use the unrounded value until the very end. And I'm going to point out that this is different than when we were looking at strong acids for calculating pH. So that's an important distinction to make. Because with strong acids, when we were calculating pH, because they were strong acids, we just assumed that the whole thing broke up into hydrogen ions and the anion. So the concentration of the acid was the hydrogen concentration, so we just plugged it into the pH. So the strong acid calculation was pretty straightforward when we wanted to know pH. For the weak acids, when we want to know pH, because they don't completely dissociate, we have to use one of these ice tables and figure out what is that hydrogen concentration. So this first step, so to speak, right, with the strong acids is just a straight one-to-one calculation, no work required. For the weak acids, we have to do this whole Ka thing before we get the hydrogen ion concentration, and then we can put in pH is equal to negative log H. So those two are really different from each other, so make sure if you are asked for the pH of an acid, the first thing to do is check, is this a weak acid or is this a strong acid? If it's a weak acid, you got to use the Ka. Speaking of the Kas, all the Kas are listed in the data booklet, so all the ones that we need for those common common acids. So you might not be given it in the question like you were with these two questions. You might be told to look it up in your table. So just be aware of that as well. And that's it for this lesson on calculating hydrogen ion concentrations for weak acids.